Hi, thanks for tuning in. I want to achieve two things with this talk. First, to convince you to think more often and more systematically about making all your apps, services, and operating system upgrades more predictable, both across time and across computers, and convince you that there are effective solutions to this problem, which scale to making entire OS reinstalls or upgrades of fleets of servers on the cloud very predictable. The TLDR is that to make systems more predictable, you have to make the state of these systems more manageable. If the state of your systems depends on thousands of giant blobs downloaded from the internet, you'll find it hard to reason about the state of your systems or to predict what it will be. We really ought to stop doing that and to instead reduce the state of our systems to the smallest set of inputs that was used to create it. That is, we should be building and rebuilding our entire IT infrastructure, always starting from the source code developers wrote for each component of it, from kernel to developer, to compiler, to library, to daemon, to application. Experimental science, we seek to build knowledge through direct observation and measurement of the world around us. This is typically done as part of experiments, during which scientists gather data in a controlled setting and later interpret this data during some kind of analysis phase. These experiments are typically done to draw conclusions about, say, a large population of individuals, but it's infeasible to observe and measure anything about all individuals in the population. And so experiments are typically done on some sample of the population. Every time the experiment is repeated, the sample will be different. Also, we have to account for measurement error. So our results will be slightly different each time. However, for well-designed experiments, we don't expect the new results to invalidate the conclusions drawn from the first time we ran the experiment. But it turns out that in a number of fields in experimental science, replicating the same or most of the same results is often vanishingly hard. In a 2006 poll of 1,500 scientists, 70% of them reported that they failed to reproduce at least one other scientist's experiment. And 50% failed to reproduce one of their own experiments. Since the early 2010s, this phenomenon is a name, and it's a name that you'll hear often: replication crisis or reproducibility crisis. This crisis in science has deep roots that can be explained by many factors. It's not a talk about science, so I won't dwell much further on the topic, but I want to suggest that we in the IT industry have a reproducibility crisis of our own. If I were to poll all of you folks listening, how many of you would say that you failed to reproduce a bug by following the steps in a bug report by a user in the last month alone? If I asked you how the last upgrade went to your fleet of EC2 instances, or on your laptop last time you typed apt-get, I bet many would tell me about all manner of failures. Games from even just 10 years ago often don't work anymore, let alone games from 20 or 30 years ago. We have backwards compatibilisms and emulation technology to make all of this possible in theory, but it's not like these games come with an unambiguous specification of exactly what environment they expect to run in. So when installing one, we're never quite sure what is going to happen. And yet, there are many reasons why you would expect reproducibility to be less of an issue in IT than it is in experimental science. For one, we're not running experiments. I don't have to deal with measurement error when trying to run an app on my computer that launched just fine on your computer. I don't have to draw a sample at random from any population. It should, in principle, be easier for me to control for the state of my system than the scientist, who has to control for hundreds or thousands of extraneous variables one way or another. Hardware fails every once in a while, but I'm dealing with otherwise mostly deterministic processes. The problem isn't that an app I just implemented won't start twice or hundreds of times on my system if I try that. It often will. The problem is that I'm just not sure that that will still be the case tomorrow. And you can't be sure that if it worked for me, it will work for you on your system. So again, software reproducibility across time and across systems ought to be easier for us than replicating the results of an experiment are for a scientist. And yeah, here we are. Can we call this a software reproducibility crisis? Can we use the word crisis? We could debate that point all day, but I hope you'll at least agree that our users are often being shafted by flaky upgrades, and that us developers are wasting a lot of time right now manually replicating instructions from other developers and failing to see the same results. We could do a lot better. So how do we do it? By day, I'm the CEO of Twig, a software company with about 50 engineers at this point. A few years ago, when we were a lot smaller, I became exasperated by how often I hear a conversation between Alice and Bob that usually went like this. Alice would say, I found a bug. Can you fix it? Bob would say, works for me. So Alice would introspect and say, well, maybe we're not using the same version of the code. Bob says, nope, I checked. Not the problem. So maybe you're not building against the same version of some third-party dependencies. Nope, that's not it, says Bob. Maybe you have IPv6 turned on, and I don't. Aha, you're right. Turns out that that was the case for Bob in this example. And this is the kind of ping pong that can go on between Alice and Bob, and that can play out over the course of an entire day sometimes. And so that's what I vow to never hear again. I vowed to never hear such conversations again. No more works for me discussions. There's no real need for them. I thought I like computers because of how much real impact they can have on improving people's lives. But I also like computers because they behave far more predictably than humans. I also like computers because there's so much that I can control, at least in theory. And surely we can make it easy to control for variability in system library versions and system configuration. Surely we can make it so that works for me is just not something that is ever said, except in the case of genuine Heisenberg bugs. Surely we can make it so that a bug is either always there or never there. Surely we can make computers behave deterministically and therefore predictably. That's the property that everyone is really interested in, predictability. So how do we do it? Well, the industry attempting to make software fail or succeed more predictably is nothing new. Because distributing apps with an RPM to be installed by all Linux users was always so error-prone. People started shipping virtual machines instead, virtual machine disk images instead, or Docker images. And a Docker image is typically more bytes to download, sure, with much more included in the image than the app itself. But at least that way, the app is packaged with absolutely all required dependencies to run the app. And at least that way, the app will run using exactly the same version of all libraries that it was tested with. And because the app will be running effectively in the same environment as the test environment, chances that the app will behave in exactly the same way as during testing, more predictably, are much higher. Docker images are a great tool. They've had an outsized impact on the industry. I would say that the main contributions of Docker is that it got most of the industry to realize two very important things. First of all, if you're going to ship software, ship it as a closure instead, which includes all of its dependencies. A closure is self-contained. It doesn't make any assumptions about the target system it's going to run on. Secondly, closures compose in ways that are otherwise impossible. If two apps both depend on different versions of glibc, then I can't run them both at the same time in the same system. But if two apps are closures, then that makes no they make no assumption about the system's globally installed glibc. So then it's not a problem. For this reason, closures are much easier to handle by users on their desktop and by ops teams in the cloud. And so coming back to Alice and Bob, if Alice always attaches the app as a self-contained Docker image in all her bug reports, then Bob knows that when he runs the app, he's doing it using the same set of libraries as Alice, the same configuration, the same data, no more unpredictable behavior. Can we do better? Okay, so launching an app that is a Docker image yields more predictable outcomes. If there was tooling that made it really easy to upload a new Docker image to some registry every time you write a bug report, that would be even better. But is that the end of the story? No, we're just getting started. So at this point, we're saying that the way to cut out works for me ping pongs is to attach bulky Docker images to every bug report. That's a lot of new bytes uploaded to a Docker registry somewhere. It's pretty difficult to cut down on the transfer costs through caching. There's no good way to cache and reuse parts of the image across multiple bug reports because of another problem. These images are opaque in the sense that we don't quite know what source code Alice started from to produce them. And even if we did know what exact source code she started from, say by also including the git revision SHA in the bug report or something, we have no guarantee that running the build script to produce the Docker image, again, will produce the exact same image as previously. In all likelihood, doing that will produce a new image, so ever so slightly different from the previous one. But it will always also be hard to tell where the difference are or why. One of the problems is that images eat up space and are slow to download and upload. So compiled artifacts can be an order of magnitude or more larger than the source that they are compiled from, especially for high-level languages. Local images, local changes to source code can lead to global differences in the object code. So heuristics to save bytes by storing related versions close to each other, like in Git, don't work well. One way to work around the bulk of a full image is to split images into layers, with the earlier layers containing things that don't change as often, like system library dependencies. Or to share partial images that don't contain the actual app itself, just the environment. But that feels really awkward. Where exactly in a complex project do you draw the line between base libraries that never change and downstream code with a lot of truth? And what if you do want to make changes to the base libraries? There's now two different paths that you have to deal with. To update a base library included in the Docker image, you have to change the Dockerfile. Whereas the code change anywhere else goes in the build system files or in the source code files. You have to deal with Docker and Dockerfile on the one hand, and the build system on the other, each with their own domain-specific language. And worse, with just an image name in hand, we need to know where to find it, probably from a specific registry somewhere on the internet. And a registry that could disappear tomorrow, it's a registry that could disappear tomorrow, at which point Bob of the future is stuck. It all feels pretty natural, if you ask me. And when I would say that the dream would be that publishing a new version of the app would be as easy as pushing a new Git branch. So the other problem is that images are hard to cache because they have no structure. VM images or Docker images are essentially opaque blobs. You can structure Docker images into cascading layers, and each layer contains files. But that's as much as we know. If two files in Docker images have the same content and the same name, are they stored only once on disk? Tell them so. Are they sent only when you download? Are they sent only once when you download both? Who knows? What we really want is more granularity on the image. We want to be able to break down the computation that produced the image into a sequence or a graph of steps, and then be able to cache the result of each step individually. Third problem is that images can't be traced back to their source. A Debian package, an RPM, a virtual machine disk image, a Docker image, what all of these things have in common is that they are binary blobs that sure are closures, at least in the case of the Docker image and the virtual machine disk image. But they are binary blobs that you are downloading from the internet with no connection to the source code they were derived from. This is very important consequence. In particular, you have to be extra careful about where you pull these artifacts from and who claims to be their author. Debian and other Linux distributions have put in place elaborate systems to sign packages and enable clients to check the authenticity of any package. But ultimately, you always have to trust the author of the package not to have turned the binary blob that you're about to execute on your system into a weapon. Executing binary blobs on your system means it forces you to distribute your trust across all the people involved along the production chain from source code to distribution package or Docker image. If you know the source code, there's no convenient way to check that the provided package really was built from the same version of the source code you're looking at. In fact, in general, this is pretty much an impossible feat because the binary blobs are seldom reproducible to begin with. And the final problem is that images can't be reproduced exactly. The thing with source code is that it's feasible to inspect it. You can pour through the millions of lines of code for, say, Firefox or GCC and check for yourself whether there are any backdoors. It's conceivable that you can build up a higher level of confidence that source code will not cause any security issues on your system. If you're confident about the source code and can't trust the package that was built from it by a third party, then the best option is to rebuild the package yourself from the source code. That's often easier said than done, and that's also true of Docker image. Take this simple Dockerfile. This is actually a snippet extracted from the official documentation. If you run Docker build once using this Dockerfile, you will get a Docker image that, being a closure, may well work fine now as well as in 10 or 20 years. But how are you to reproduce this image from the Dockerfile? If you lose the image, how can you recreate it? If you have the image, how do you know for sure that it came from this Dockerfile? It's likely not going to be possible because there are a lot of hidden inputs to the Docker image building process. For one, Docker images are built in layers. The Dockerfile here mentions a label for a base layer, but exactly which base layer this label refers to is unclear. The hidden input here is time. Depending on the moment at which we evaluate this Dockerfile, we're going to be picking up this base layer or some other base layer. Ubuntu latest can refer to the label Ubuntu latest can refer to something today that is not at all what it refers to tomorrow, when a new version of Ubuntu gets released, or even when Ubuntu applies a security patch to one of the base libraries. And secondly, build actions can do anything at all. In the second line of the file here, we're downloading arbitrary data from package repositories somewhere. We could have caused arbitrary side effects to the world, like sending a post request to some HTTP endpoint to launch missiles. We can ask the system for a random number or the current date, or do some number crunching in a Lambda function on the AWS cloud before moving on to the next build action. None of this is reproducible. All of this essentially depends on unspecified inputs from somewhere in the internet that can change over time. Let's try a mini game. Imagine that your requirement is that we have to prepare for the alien invasion. All humans have been destroyed, but our Startup service still works. If only the aliens could get their hands on the manuals. If we want our software to survive us, to survive even the existence of the human race, we need to engineer our apps to be really easy to launch and really easy to recreate from scratch. So imagine that as part of the invasion, most hard disks suffered irreparable damage due to the aliens using some kind of alien EM pulse weapon. That's not to say that all code is lost. Everything hosted on GitHub is still there, at least in the version that was stored in the Arctic Vault. Remember that little icon on most GitHub user profiles? So how do we design our project to survive the alien invasion? So first of all, you'll want all the inputs to build a complete closure from source to be stored in one place. If everything is in the Arctic Vault, ideally in a single repository, chances are that if some of our code survives, all of our code survives, and so the aliens have a chance to build our code and run our app, even if most other software is lost. If the alien chances upon our code repository in the vault, they won't know what computer to run it on, or what emulator to use on top of their alien computers. So we need a modicum of metadata, but this is really, metadata reduced to its bare minimum. It's metadata describing what hardware our app was designed for. And as part of this metadata, you basically want this to be an extremely short README file, because the aliens don't understand English anyways. So you just want this README file to give the name of the command to type to build the entire app, and another command for running the app. To build our source code, we need a compiler. To execute that compiler, we need an operating system. So for our source repository to include everything we need means that we need all the source code for a compiler in there and all the source code for our operating system too. Remember, we can't assume the aliens know anything about our software, so we're starting from scratch. This means that parts of our repository need to be built before other parts. We need to build the operating system first, then we need to build the compiler, although we also need a compiler to build the operating system later. But once we have a compiler running inside the environment it needs, we can start building our source code. There's an order to things, and we need each step to be cacheable, so that if we have to rebuild the operating system, then maybe we have to rebuild the compiler as well. But if we change the compiler used to build our source code, we don't want to have to rebuild the operating system. We need a full dependency graph for all the steps in our code. But better yet, if the dependency graph is fine-grained, so that we can cache many small steps individually and only rebuild many small steps and only rebuild the very minimum that we need to rebuild if something changes. Now, let's say the aliens built our compiler once and then build our source code with it. Let's say that later they decide to rebuild the compiler without using the cache. If the process of building a compiler is not completely deterministic, then this time around the aliens may end up with some slightly different compiler. Will this new compiler create exactly the same app from the source code? It's unclear. Now, what if the aliens decide to reintroduce the cache? Then rebuilding our code would use the old compiler, not the new one. Therefore, is it safe to use the cache? It's unclear. What we need is for the function that creates a new compiler to truly behave like a function. It should be a pure function of its inputs, i.e. deterministically produce the compiler from the source code of the compiler, and any declared dependencies, and only that. Then it becomes safe to use a cache. And lastly, if we're going to build such a robust cache-safe graph of deterministic computation steps, it would be really nice if we could express that graph using a single declarative language. Think back to the discussion we had earlier using static Docker images to provision seldom changing third-party dependencies versus keeping all our other dependencies in our build system. This is an artificial split of the global dependency graph, which becomes harder to maintain. We want one graph expressed with one language all the way down, ideally. In summary, we want all the inputs in one place, minimal metadata, only the hardware dependencies, we want explicit dependency graph, we want the dependency graph to be fine-grained, to maximize parallelism, and to have a global view of the dependency graph that we can cache effectively. We want the graph, evaluation of the graph to be cache safe, and that requires each computation step in the graph, each node in this dependency graph to be a deterministic function. And the last requirement that we had was that we want a single description language for the entire graph. The alien invasion is just a figment of our imagination, but we can realize many of the goals today. It's mostly possible using Docker in a certain way, but it's also how Nix, one of the most active projects on GitHub, was designed to be used. Nix is a system for executing functions built as graphs of deterministic steps and keeping track of the result. You can use it to reliably reproduce Docker images from source. We've also used it to reproduce Windows virtual machines. And this laptop's entire operating system, including all of the system libraries and configuration files /etc, is the result of evaluating a graph of nearly completely deterministic functions, starting from nearly only source code for everything, to the point that if you evaluate this same graph on your computer, you are very likely to get a near byte-for-byte identical operating system to mine on your computer, and without downloading, or practically without downloading any binary blobs from the internet. This is all starting from source code. What I'm going to show you next is part of the content of a single Git repository on GitHub. The README file is very short. It tells you about a single command you can run to rebuild my operating system on your computer, or indeed the aliens to do so once we're all dead, despite them having zero knowledge of what Linux is or how it works. You can go on GitHub today, look at the, start from that README, look at the other files that are in this repository, and you will be able to recreate the same operating system that I have on this laptop on your computer. So first off, the README, short file saying there's just one command you have to run to end up with the exact same operating system on your computer's mine. The first two commands are just putting the configuration files in the right place so they get picked up by Nix. Single command. Then we have a number of configuration files, and these are all configuration files that we're feeding to Nix. They're in a single place. They're all in this repository. And this is where I'm specifying what I want my system to look like. I'm telling Nix about where my partitions are located and what I want my computer to be identified as on the network. I don't want to have to edit a dozen different Unix RC files in different formats to do this, because those files are a function of the Nix configuration that I write here. There's more to configuration. I can my locale, set things like time zone or preferred keyboard layout for each user. All of that goes in the Nix files. And we can even configure far more than that, all the way to the services that run on my laptop. And Nix will produce the configuration files, the daemons and applications that they expect. In this example, I'm telling Nix how I want my Emacs to behave. I'm saying I want printing and what printer drivers to use, and I'm even configuring my graphical display and login manager. Nix will run some deterministic function to create the configuration files for Emacs from the specification for the printing daemon and for the login manager. And here's the crucial bit. None of this would be terribly reproducible by you if we didn't also have a way to tell Next exactly what functions we want to use to interpret the specification of my operating system. It's no fun if the specification is now going to be interpreted by some binary blob I downloaded from the internet. Remember, that's bad. What I'm doing here is that I'm saying to Nix that my entire operating system description is self-contained. The functions to interpret my specification are basically a mix of C++ code and a lot of bash, but they are all found either verbatim or by reference in this one repository in the URL field of this JSON file. They're all either found in this one repository by reference or literally. If we're going to point to repository, we'll also want to be pointing to a specific revision, a specific version of that repository given by the commit SHA in this JSON file. So coming back to the earlier scenario with Alice and Bob, how does this apply to them? Alice and Bob don't need to be running on exactly the same operating system, configured in exactly the same way to be able to collaborate together. But when Alice is sharing a bug report, she does want to be 100% sure that Bob will understand unambiguously how she built the app that has the bug she spotted. She may or may not need the graphical display or the kernel to be the same, but even if she doesn't, she at least wants to make sure everyone is using the same Go compiler, the same C compiler, the same tools to monitor performance issues, and the same debugger. And again, Nix can help with that. Just like I previously wrote down a specification of my entire operating system as closure, now Alice can write down an unambiguous and fully reproducible specification of the development environment they use, or indeed of the app she built and wants to attach to the bug report. Bob doesn't need to download any big blob from the internet to see for himself what happened to Alice. He just needs to download the same specification as she did and run Nix to evaluate the dependency graph that was specified by the specification. Sure, it's a large specification if it's describing everything from which glibc to use to what compiler to where the source code is found for the developer tools they need, such as GDB. But that specification is nonetheless a much smaller piece of state than binary blobs. And it's a piece of state that Bob can understand and read, unlike the hex codes of a binary blob. So that all works well, but there are limitations to Nix currently. There are things we could do to minimize the amount of binary blobs we rely on even more. They do exist. Something I mentioned earlier is that you need a compiler to build an operating system and an operating system to run a compiler. Even just to build the compiler itself, you need some. At some point, you have to rely on a binary blob. And currently in Nix, we do have several big binary blobs. Surprisingly, one of them is a blob for the compiler. And that's rather unsatisfactory because it means that we can't reduce the state of our system to less than about 23 megabytes of trusted binaries, at least. And that's a lot to trust. The good news is that there are efforts afoot to significantly reduce the state even further. Several folks in the Geeks community, a fork of Nix, are getting close to bootstrapping the entire thing, from my operating system to Alice Bob's development project to everything else, using just a few kilobytes by chaining increasingly complex interpreters and compilers. Great topic for later in the discussion. Another great topic for discussion is figuring out good strategies to truly achieve 100% byte-for-byte reproducibility. Nix currently uses a number of strategies to make steps in the dependency graph fully deterministic, like sandboxing and isolating computations from the network during build time. But in practice, we fall short, simply because there are always hidden inputs to functions in the form of execution timings, which computations inside of sandbox can observe, or other sources of randomness like the order of files in the file system, or asking the kernel, or simply asking the kernel for random bytes. And so to conclude, what we did is say, hey, let's make our systems more predictable. That's going to help our users save time and our developers save time. Because there are just that many fewer rabbit holes they now have to go down anytime they consider upgrading their operating system, installing a third-party app or library, or modifying third-party dependencies. If everyone can count on something just working, if it worked once for someone else, we all get to go home a little sooner every day. The key to making apps more predictable is to distribute them as closures, and closures behave more predictably and also work better together because they compose better. We saw how endowing closures with internal structure makes sharing substructure possible and therefore caching more effective. We saw that if we make producing closures a deterministic function, then we make it possible to trace them back to the sources they were produced from, and make it possible to reproduce them byte for byte or nearly byte for byte to check that a given closure really does come from the source we think it does. Closures are a great way to make Alice and Bob work together. If Alice always attaches a closure to all her bug reports, we spent some time thinking about what design patterns we'd use to make software that is so reproducible across systems and across time that it could well survive us all, even when the aliens come to put us all out of our misery. And it turns out that what works for long-term reproducibility also works for making the bug reports Alice and Bob share with each other a lot more effective. The two key ingredients here is shipping software as closures and making the construction of these closures deterministic. It is these two ingredients that make it possible to reduce the size of the state that characterizes systems, or miniaturize these states. But that begs the question, where else do you see these two age-old ingredients being useful? We talked a lot about reducing the size of our development environments and of our operating systems, but could we perhaps apply the same principles to the runtime of apps? What would we gain in terms of debuggability if the in-memory state of our apps or services was always a deterministic function of a small amount of state? That's what event sourcing is all about. Thank you for your time and looking forward to the discussion.
Thank you, Mathieu. And yeah, so let's see. Do we have any questions? While people coming up with questions, I just know that. So first, if anyone feels like enabling their cameras, that's always nice because you feel sort of less detached from what's happening. And also, if anyone hesitates if their question is sort of relevant, or just any sort of comments or impressions of what you've just heard of, I think is fine. So we will be happy to hear your war stories about trying to reproduce bugs or something like that. Yeah, so we have one question on Clouder. It's a silent question from Yulia Belякova. She asks, is it possible to not specify the entire list of dependencies? If yes, what happens?
All right, so do you hear me well?
Yes.
Okay, and no echo?
No echo.
Excellent. So that's a good question. So I would say that if you don't include all dependencies, then your dependencies have been stated incorrectly. And a good feature of these kinds of systems of mix and build systems in general. So for example, if you take Make or Bazel or I mean any of these build systems that are out there now, and there's a lot of build systems. Some of these build systems are good at detecting whether your dependencies have been stated incorrectly, and other build systems are not. And I think that what gives build systems a bad rap is that they're so often very finicky to work with, because so often dependencies were not stated correctly, but no one ever noticed because, you know, in most cases, things work. So for example, with make, if you forget to state all the dependencies of a particular target, but those dependencies also happen to be the dependencies of some dependency further up the graph, then things are mostly going to be okay until you start modifying a file somewhere in the dependency graph, and you know nothing gets rebuilt the way you expected it to. So it's very pernicious type of bug when dependencies when the list of dependencies doesn't get stated correctly. And so it's a real feature of the build system to basically always fail if the dependencies were incorrectly stated. So, you know, that's a bug where you don't want things to sometimes fail. You want things to always fail. And that's what Nix does. Because it basically copies your dependencies into a special area to make them visible to the build, to the action, to the computation. If you don't state if you incorrectly state the dependencies, if you miss out one or two dependencies, then those will simply not be visible to the computation, and therefore the computation will fail. If it doesn't fail, then perhaps the dependency wasn't necessary to begin with, and so there's no problem.
Sounds reasonable. Yeah, I think I
answer
had
your question, Julia, or
yeah, Julia wants to
what
follow up.
would you expect to hear regarding that question?
No, that makes sense. Thanks.
Cool.
Yeah, I guess some sort of a hidden question under this one would be, is it possible to sort of expect the build system to infer some of the dependencies that you sort of either missed or you didn't sort of want to just, you know, manually enumerate, which might be tedious. So is it a feature that, I don't know, Nix has or some other build systems have these days?
Yeah, so in Nix, there is a little bit of essentially auto detection of dependencies. Mm-hmm. And so, but these build systems are quite difficult to build, and they're quite difficult to make performant. Although some, famously, there's a build system called Shake, that's backed by a paper that was published at ICFP some years ago, which actually manages to do this. And so what Shake enables you to do is it enables you to run a computation that detects new dependencies and then dynamically adds new dependencies to the dependency graph as we're going along. This is a feature that does also exist in Nix. However, it's discouraged to use it because the way it's implemented right now in Nix, you basically kill all parallelism. So there's basically a giant, effectively like a giant lock that's acquired. And so it kills all parallelism. It's generally bad for performance. Yeah, I mean, the community's just basically built an aversion towards it. Systems like, you know, you mentioned Bazel. Bazel, for example, does not have something like that. Mm-hmm. And so what people do in these other systems is that they run some tools offline. So for example, the Go community, when, you know, people who want to build Go using Bazel, they have this tool called Gazelle that they basically call manually before calling the build system. And Gazelle will generate the dependency definition files for you, and then you run Bazel. But Bazel will never run an action that can dynamically detect, as it's evaluating the graph, detect new dependencies.
Yeah. Running something twice, or like running a first one tool and then another, sounds like a reasonable strategy, I guess.
Yeah, but the risk there, right, is that what if you forget to run the one tool before the other?
Yeah, that's
so fair. Then what you could do is that you can write a wrapper script that says, well, I'm never going to call Bazel, for example. I'm always going to call this script that unilaterally calls Gazelle first, just in case, and then calls Bazel. But that's a very pessimistic strategy because you know, Gazelle, the kind of analysis that it does to generate the dependency information, it's kind of non-trivial. And so, you know, but you're rerunning that analysis every time you're calling Bazel. And imagine that you have thousands of source files, which is not uncommon. In fact, in the use case that Google has, Google first created Bazel, they have 2 billion lines of code. And I don't know how many of those 2 billion lines of code in a single repository, by the way. And I don't know how many of those lines of code are Go code. But yeah, you can imagine that just, you know, calling an analysis, a global analysis like that unilaterally is not really a good idea.
Not a good idea, I agree. So we have a couple of questions in Zoom. First one I see from Asif. I can voice the question, but if Asif wants to sort of tune in and maybe ask it, that's also fine. So it's a short question. I can ask, and then maybe you will follow up, Asif, if you want. How hard is it to modify or add new features into an already running system?
So, well, Asif, maybe you can tell me a little bit more. What do you mean by already running?
Yeah, that's a good question. So sometimes people can't use their mic. So I see Asif is on the call. If you can unmute, please do. If you can't, yeah, I guess we're out of luck for getting any.
So in general, I mean, I'll take an example. Let's say that what you created is like a set of EC2 instances, and so, you know, you created it's the result of running some specification that says exactly in which state these systems should be. Now, let's say that you want to hot patch these systems because, I don't know, there was a configuration problem actually, and it's you know, you just want to fiddle with the state of the system on the fly. So in general, that's actually a pretty bad idea, because now, you know, for example, let's say you make the change on one server and you have 10 servers and you forget to do it on the 9 others. Now there's configuration drift. There's, you know, the state of the 10 servers is now not identical anymore. And there's nothing to tell you that that's the case. So it's something that you can do, just like on any other system. And it's something that you can do without applying a new upgrade through Nix, or, like, you know, tearing down the entire system and starting from scratch. But it's probably something that you don't want to do. Now, if you simply want to upgrade the system, so for example, you would say, okay, I created the new system and it's there, and I just want to, for example, move to a newer version of the SSH server. Well, you can push that upgrade, and that upgrade will be applied atomically. And that's a really important feature of Nix, is that it's either, the upgrade is either fully going to work or not at all. And so, you know, you don't need to worry about, you know, the powers being on for your server throughout the upgrade, because, you know, as is the case for Debian, for example, or for Arch Linux. I mean, I've hosed my systems a few times before because I was in the middle of an upgrade when, like, you know, the power ran out on my laptop. This is not something that would happen on Nix. Now, a related thing that I might say is that so in general, you don't touch your systems while they're running, except if you deliberately change the specification of their state and you reapply that specification. But you know, you are going to have a little bit of configuration drift anyways, or state drift, let's call it, in the form of, for example, log files that are just going to accumulate somewhere. or a temporary file somewhere in /tmp. And so what some people do is that they basically say, well, so that I'm sure that all of my systems are always in exactly the state that I expect them to be, I'm going to set up a job, like a cron job, let's say, that's going to at the end of every day or at the end of every week is going to just kill the system completely, just destroy it. And that way, you rebuild it, and when you rebuild it, it's in exactly, byte for byte in the state that you expected, with no log files lying around anywhere, or temporary files. And crucially, that the existence of these random files has not somehow become crucial to the uptime of the system because something happened. So that way you keep your confidence that you can always recreate your system in the current state, because actually that's what you're doing every 24 hours.
Makes sense. Yeah, I think Steve had a follow-up story sort of in the chat, and basically, yeah, I think you mostly addressed it. So I think the essence of his question was, what would you do if you have a system that is already running and you have to modify its configuration, I guess, and then so what would be the way you stop it and then respin it, or sort of with the new config? So is the downtime inevitable, or like is there some way to make it really look as a momentarily update? Like,
yeah, so sometimes you have to update you have to update the kernel, and so then well, you're going to have to reboot the system.
Sure.
Well, you hope that you have a load balancer somewhere, so that if you really want a zero downtime, then you create two identical servers, or say one server with the new state, and then you just switch all requests to the other server while you're rebooting the one server. I mean, just the way you would do it with any other system. But short of kernel upgrades, I mean, most changes that you would make in Nix to a system don't require any downtime, don't require rebooting anything. You can just apply it. It's pretty quick because Nix knows exactly what the current system, the current state is, and so it can safely just move to the new state, without fear of things sometimes working and sometimes not. And so it will basically do the exact minimum stuff that it needs to do to move to the new target state. And so then let's say that you have let's say that what you want to update is like an HTTP server that's running and serving requests. So let's say it's Nginx, and you want to move to the new version of Nginx. So what we have is these TCP wrappers that basically allow you to basically stand up the new Nginx at the same time as the old Nginx. And then you just have, at the very last moment, a switch between the two servers. And again, there's really no downtime there because the two processes, in fact, have even been booted. Both processes are running, both servers are running, and you just have this very quick switch between the two.
Cool. Yeah. So we have another question from Robert Biddle. I see Robert on the call with camera on. If you want to ask it yourself, you could.
Okay, sure. So the main theme here is predictability, but in security work, predictability can be problematic because it gives attackers various kinds of advantages. And so we've developed strategies like memory address randomization to reduce this, this curious part of the attack surface. What do you think the impacts on the strategies that you've outlined are for security approaches like that?
Yeah, so that's a really great question because maybe as you say, you want the state on the disk to be slightly different, And so perhaps you want to have basically some kind of equivalence relation. So you want to say things are the same modulo what should be different. So for example, maybe the order of the dynamic libraries when they're linked into they're linked into memory or something. I mean, you mentioned specifically though things like address randomization. I mean, these are runtime variations, right? And in Nix, we're mostly concerned with the state of the installed system. So when you're running the application, I mean, there's nothing stopping you from randomizing the addresses at load time, for example.
But I mean, in your introductory remarks, you were talking about the "I can't reproduce it, works for me" issue,
Right?
And that's directly relevant.
Yeah, yeah. So it's two. I think there are potentially two conflicting goals here that you have to kind of manage. And so you could say, okay, well, in the name of security, I will allow some variation, but it's structured variation. It's variation that's only a specific way. So, for example, with address randomization, you're only changing the location of shared objects in the address space, right? And yeah, maybe that could. I mean, that's unlikely to create differences in runtime behavior. And so I guess, but sometimes it will. So there's no absolutes here. Sometimes you may have to give up some predictability in order to get some security guarantees, for example. Well, no guarantees, but
right. So the bigger picture in the security community takes inspiration from ecological systems, right? And what they're concerned about is kind of monoculture, where if you have exactly the same genome of same species in large crops, for instance, then some attack of a bacteria or some insect pest or something wipes out the food supply of the whole world. So while memory address randomization is one aspect, the general principle is that ecodiversity acts as a kind of global defense against various forms of attacks.
Yep.
So it strikes me that in some ways this is always going to be in tension with predictability.
Yeah, and I think that what you perhaps want is not so much absolute predictability always. It's the only thing that you want, but more control over how much predictability. So, for example, sometimes you want diversity, sometimes you want predictability, and if you can at least have control over that, if you don't have like incidental variability that, for example, adds nothing from a security perspective, it just makes everyone's life harder. Well, maybe you want to remove that kind of that kind of variability. So in other words, coming back to the scientist, he wants to control variables. So what you're saying is maybe some variables we don't want to control them. We're free to let them take on whatever value they want. And then there are some other variables that we very much do want to control. We very much want to pin them.
Mm-hmm. Okay, thank you.
Good. So let's see. Do we have any more questions? I don't see anything on Clouder.
I have a question. So I was wondering, the operating system, like if you make upgrades to the system itself, is it also versioned? And if you, like in the build script, from what you've shown in the talk, it seems you just say, oh, I'm using NixOS without any extra information. So how does it work if the operating system changes? Do you just use the latest version, or can you specify that? Or does it not matter and it's like always guaranteed to be backwards compatible?
So when you're using NixOS, what you can do is you can specify basically exactly which version of NixOS you want. And so, for example, if you have a Git repository that basically contains the full specification for the NixOS that you want today, you can like git pull in that Git repository at the end of the day, and now you have a new specification for a new NixOS. And so then you can say, well, I want to switch to that new NixOS, and maybe that new NixOS has a new kernel version. And so maybe, you know, that's a kernel version that you want to activate. And so anytime you basically say, you run that command that I had in the README for that repository that it shows that contains the configuration, the NixOS configuration for my laptop. That, you know, that command says something like NixOS rebuild switch. Every time you say NixOS rebuild switch, what that command will do is that it will create a new NixOS on the hard disk that's completely separate morally from the previous one, except that, you know, in practice it's sharing a lot of what's in common with the previous version of NixOS. So it's not going to explode, you know, disk usage. However, what it's also going to do is that it's going to add a new entry to your bootloader. And so, you know, next time and it's going to mark that as the default. And so next time you reboot, you will automatically move to the new version. But crucially, any old version hasn't been destroyed. It's still around. And so any time you say NixOS rebuild switch, you can do that, for example, 300 times in a year, and you would have those 300 entries in your bootloader, so long as you don't, you know, run any special command to delete them. They're still around. And so if an upgrade, if, for example, moving to a new kernel breaks, let's say that, you know, they changed the webcam driver or something in the new version of the kernel, and maybe your webcam doesn't work anymore. You're like, oh man, that sucks. I want my webcam again. So then you can just reboot and choose the previous entry in your bootloader.
And I have, sorry, don't want to, Sophia says to rise the session, but one more question. So if I have several, like maybe I want to build several artifacts that share a lot in common, so maybe they're using the same operating system, like the same libraries, but then I want to have like maybe one system with C, another with Haskell, and another with something else, and do different things in those three things. Is there a way to share the common thing on the disk so that I don't have 3 copies of the same core infrastructure, or how does it work?
Yeah, so you can think of that situation as akin to, you basically have one giant dependency graph. Like you have this giant specification that's basically for a dependency graph, that's basically a collaborative specification. This is what, so there's a repository in the NixOS organization on GitHub called nixbkgs. And it's a huge specification that includes like dozens of thousands of dependencies. And some of them are Haskell dependencies, some of them are C, some of them are Python. And for any one project that you're going to have on your computer, you're going to say, well, for example, in this one project, I want to, this is a Python project, so I'm going to use a bunch of Python things. And by doing so, you're basically evaluating part of this very, very large dependency graph. You know, you're forcing the you're evaluating it on your system, just the local part of the dependency graph. And to the extent that let's say you have two completely different projects that have two completely different dependencies. When you enter the one project, it's basically going to pull in more stuff on your hard disk, stuff that was never there before because the first project that you had completely different dependencies. But in practice, there's always going to be something in common between these projects. So, for example, even Haskell projects depend on glibc, the C standard library. Even Haskell projects usually depend on on zlib or libz for compression, decompression. And this is also a very common dependency for most other projects. And but in these cases, the zlib that we're talking about, there's usually one zlib in the entire dependency graph, and it's just that the one part of the dependency graph, which is kind of the Python world, depends on the zlib, and then this other part of the dependency graph is kind of the Haskell world, but they both depend on the same zlib, and because they both depend on the same zlib, that zlib will be shared across all your projects.
Mm-hmm. So all my Nix projects on the same machine will use the same Nix infrastructure, and like if something is already downloaded and built, it will be reused for all different Nix projects.
Yes, if you're using the same specification of this of the dependency graph. Now remember that this is a huge dependency graph that's collaboratively edited by many people on GitHub. And it's possible that for one project, you're going to use the dependency graph as it stood in June 2020, whereas for another project, you're going to use the dependency graph as it stood in, say, December 2020. Some things are going to be in common between those two versions of the specifications, in which case Nix will reuse things. But oftentimes, those specifications will be so different that nothing will be in common on disk. I'll give you an example here. Nearly everything depends on glibc, and if someone made some updates to glibc in between June 2020 and December 2020, then when you start a project using the December 2020 specification and start saying, hey, I want all those dependencies to be provisioned, you're going to find that everything is being re-downloaded that you thought you had downloaded before. Well, sure, because these other dependencies from before, they were using an older glibc.
Yeah, makes sense. Thanks.
All right. I don't see any more text questions. I have a couple of mine, but before I ask them, maybe we should make a minute of awkward silence or half minute of awkward silence when anyone who is on the call can maybe still come up with some questions.
Don't raise hand from Hillel.
All right.
Yeah.
I have a question. Maybe it's more a question to the Nix developers, but I was just wondering, so since if you want to have the reproducibility, right, then you have to have everything inside the Nix packages, right, and a lot of the software, and you also need to have some kind of a hacks that you can have actually multiple versions of libc on your machine, and multiple versions of the other dependencies. So if the package that you want to use or the piece of software, strictly depends on the file system hierarchy in Linux, and expect something to be on a certain path, then you need to do some patches, right?
Yeah.
And and that's, I was always wondering how that really works, right? Because a lot of software nowadays, especially when people are a little bit concerned about security, they will basically somehow sign the source code. right? But now I need to patch it. I guess other distributions do this as well. But but now I suddenly need to sort of believe that what I'm getting from Nix is actually what the original software is, modulo the extra changes, and then you need to have somebody who really understands the code and how this process works, because it seems that must be a lot of work.
Well, sometimes it is a lot of work. I would say it's usually a lot of work when the software has been kind of poorly written, or is making a lot of assumptions. To me, you probably don't want to write software in such a way that you have hard-coded paths all over the source code that really wants something, for example, to be in user share or user lib, some global path on a file system. And if you're going to have these hard-coded paths, at least define them in a single location so that it's easy to patch them, to change them, rather than just duplicating these paths all over the code base. So you're right. There are some software out there that's just not very easy to patch. But every Linux distribution does some patching. Some have a philosophical idea around trying to keep the patching to a minimum. And by and large, that's also the case in Nix. I mean, we do patch software, but it's usually just the minimum to get it working the Nix way. Every Linux distribution does some patching, and sure, Nix does this too. It's, as you're concerned whether it's a lot of work or not, I would say that again, it really depends, but on average, it can't be that bad, because if you look at the number of packages that exist on in the Nix OS distribution today, there's actually a website called repology.net, I think, which basically compares all major Linux distributions and has statistics about them, like how many packages do they have total in this distribution? How many of those packages are up to date? And I mean, these statistics change every week, but last time I looked at it, I think NixOS was basically the distribution with the most packages, and one of the most with and one with the most up-to-date packages. So it's not like we have thousands and thousands of packages, but then no one maintains them. We have a lot of actively maintained, up-to-date packages. So sure, it might be a little difficult to patch things to work the Nix way, but it can't be that bad. Otherwise, you wouldn't expect to see NixOS to basically be the leading distribution in terms of number of packages available.
Right. Well, I mean, it's not that, I would like to a hard code path, but I have to live with the software which has it hard coded, and it's not always easy to, fix it upstream, right? Because
yeah,
it's just
there are some options. So, for example, there's this thing called build FHS env. So for let's say you have proprietary software that you download. It's a blob, and so you really can't patch it. It's there. There's like paths hard coded in the ELF file. There's nothing you can do about that. Then you can run that in basically a bespoke sandbox with a basically very with a bespoke view of the file system. So Nix can basically wrap software that's kind of particularly ill-behaved to make it believe that it is in a so-called FHS compliant file system. FHS standing for the standard file system hierarchy in Linux. And then there's also another solution, but that's a really hacky one, and it's not a recommended one, and it's called patch elf. So sometimes people do that. They have the elf binary. That's all they have. They don't have the source code. And in some situations, it is possible to actually patch any hard-coded file in the elf file without breaking the binary. But this is very hacky and very dangerous.
So if I can just have one more thing. So when you said that, there's a lot of packages in Nix, but that also means that because, if you want to have things reproducible, it's not just, the dependencies, like, let's say I work on R and now I need to, if I want to have my environment reproducible, then I need all the R packages, right? And their dependencies in. So basically you have to also mirror whatever is in cran or whatever is in package or whatever is in PyPy or, Maven and, all of these, right? So that's quite an effort. I mean,
indeed. And I think that the best practices in this area are kind of evolving. So for example, some Nix users are very happy to use Nix, but they don't want to use Nix as basically the universal package manager that handles all of your R packages and all of your Haskell packages and all of everything, right? And so they would basically delegate the handling of R dependencies to the R package manager. But other users go the opposite direction. They very much do want to import all of CRAN, all of package, all of CTAN or CPAN, and so on into Nix. And there are some pretty good tools for that. So for example, Twig develops this tool called Poetry to Nix, which basically does that for the Python ecosystem. The concern is that Nix as a distribution will basically become gigantic, because if you look at the number of packages that there are on CRAN, I think it's maybe 15,000 packages. And for package for Haskell, it's a similar number. This is a very big number. So something else that we're developing is called Flakes. And the thing with Flakes is that it allows you to basically federate the definition of this build graph. So you don't have just NixPKGS anymore. You can have like NixPKGS, which contains like Firefox and glibc and all of the regular things that you expect. And then also have the R community maintain their own Nix mirror of CRAN. And they do it however they like it. And they can iterate on that independently of NixPKGS. And then they can compose that using the Flakes mechanism. And so I won't delve too much into the details of what Flakes is and so on, but there was a talk given by Elko, one of our engineers who invented Nix incidentally, last year at NixCon, which is worth a watch. And there's an RFC that's also detailing a lot of the technical details.
Okay, thanks a lot.
Cool. So I think we have run out of time for our session, for this take at least. So I thanks everyone for participating. Thank you, Mathieu, for the talk and for answering.
Yeah, sorry, thank you for all the great questions.
Could I ask one more? If
sure, unless we are yeah, I hope we are not kicked out from the Zoom room. I don't know what's the protocol here. I know we have it for 40 minutes, and 40 minutes run out. But if no one kicks us out, we are I guess you can go ahead.
Oh, there is a word session. Yeah, if people need to go, but Zoom seems to be free.
You can write your question in Clouder, and we can address it in the next take of this session, which will happen in 12 hours. Yeah, if that sounds right. So
yeah, I mean, I'm available, but if we're going to get kicked out, I can answer that question.
And Zoom seems to be available.
Yeah, I guess you can ask.
Yeah, I was wondering more generally, like there is some effort to build the tools or frameworks, cloud systems to help in storing artifacts. I don't remember the name of those things. I'm not sure whether they were based on Nix or Docker, but I was wondering your thoughts about collaboration on such things for scientific community, like to store artifacts and be able to access them, and what kind of infrastructure needs to be there to support
software artifacts in particular, right?
Yeah.
You mean for the science community specifically, or?
Yeah, so scientific so lately, at least in some computer science and software engineering, there is this thing called the artifact evaluation, where people prepare their artifacts for the research papers that they're writing. And most of the time we just use some like VirtualBox, sometimes Docker, maybe sometimes Nix. But it's still quite hard because you need to find where it's stored, if anywhere, or maybe the website's already dead. And it seems there is some effort to have some cloud solutions or a big website where people can upload this.
So there's a lot of different ways to use Nix, and a quite popular way to use Nix is to basically say, you know what,